Good day, Dr. Ryan. I am Marky Reyes from BSCPE 41. In this discussion, we will unravel the intricate workings of the Central Processing Unit, or the CPU. We will delve into the evolution of CPUs, tracing their development from the early stages to the advanced processors of today. Understanding the operations of the simple as possible one or SAP1 architecture will be a focal point, exploring its fundamental functions and programming principles. Throughout our exploration, we will encounter tangible examples to illuminate the concept discussed, providing a comprehensive insight into the fascinating world of CPU architecture and programming. Now, let's start on how the Central Processing Unit works. The Central Processing Unit, or the CPU, often referred to a computer's brain, orchestrates complex tasks through a series of well-defined stages known as the fetch, decode, execute cycle. This cycle begins with the fetch stage, where the program counter guides the CPU to retrieve instruction from memory. The fetch instruction is then loaded into the instruction register, initiating the decode process. The control unit identifies the operation to be performed and any associated operands by unraveling the instructions opcode. Moving to the execute stage, the CPU performs the specified operation using the arithmetic logic unit and may access memory through the memory address register and memory data register. If the instruction produces a result requiring storage, the write back stage ensures the data is stored in the designated location, and the program counter is updated for the next instruction. Throughout the stages, registers like the accumulator and index registers act as a temporary storage units facilitating data exchange. The CPU's internal clock governs the timing of these operations, while cache memory enhances efficiency by storing frequently accessed data. To optimize processing further, some CPUs employ techniques like pipelining, allowing overlap of multiple stages in the cycle. In advanced systems, multi-core processing enables simultaneous execution of multiple instructions using multiple processing cores. In summary, the CPU's orchestrated interplay of registers, the ALU, memory access, and control units coupled with clock synchronization and memory optimization empowers it as the computational powerhouse of a computer. The CPU's efficiency significantly contributes to a computer system's speed, responsiveness, and capabilities, enabling the execution of diverse tasks and running complex applications seamlessly. For example, imagine you are running a word processing application on your computer. When you click to save a document, the CPU springs into action. First, in the fetch stage, it locates the instruction for saving in the computer's memory using the program counter. The instruction is then loaded into the instruction register. Now, in the decode stage, the CPU's control unit deciphers the instruction, recognizing it as a save command. It identifies the necessary details like the file name and location from the instruction's opcode. Moving to the execute stage, the CPU utilizes its arithmetic logic unit to carry out the save operations, potentially accessing memory through the memory register and memory data register. If the operation produces a result, such as confirming the file is saved, the write back stage ensures this information is stored appropriately. Throughout these stages, various registers like the accumulator and other act as a temporary storage, facilitating the swift exchange of data during the execution of the save command. The CPU's internal clock dictates the timing of these operations, Optimizing the process, modern CPUs may use techniques like pipelining, enabling efficient overlap of multiple stages. In multi-core processes, the several cores could collaborate, allowing your computer to handle multiple tasks simultaneously. In essence, the seamless coordination of the CPU's components ensures that your save command is executed swiftly and accurately, showcasing the efficiency and power of the CPU in everyday computing tasks. Let's move to the evolution of central processing unit. During the mid-1960s, a miniaturization revolution ignited the integrated circuit, leading to a pivotal shift in society. In 1971, Intel launched the 4004 CPU, a semiconductor marvel with 2,300 transistors, ushering in a new era. Fast forward to 2017, the Intel Core i9-7980XE boasts over 80 billion instructions per second, showcasing a remarkable 900,000 times increase in processing power. CPUs process data based on binary representation with word size at the core of their architecture. The original 4004 had a 4-bit word, while modern CPUs operate on 64-bit or 32-bit words. Instructions fundamental to all computer programs follow a 3-step process: fetch, decode, and execute. The CPU's operation is synchronized by a clock, and as CPUs advance, clock rates increased. However, optimizing clock cycles became crucial for efficiency, facing challenges like unpredictable results and heat buildup. The series explores the evolution from the Intel 4004 to the Intel 8086 in 1978, a 16-bit CPU contributing to complex instruction set computer or CISC architecture. It delves into CISC versus reduced instruction set computer or the RISC architectures, highlighting the advantages of CISC. The 8086 success is tied to the IBM PC in 1981, solidifying the 8086 legacy as the standard for personal computing. Microsoft Word's development in 1981, initially on MS-DOS, marked a shift towards mouse-friendly application. The 1980s and 90s saw a demand for 32-bit processors. The 8038-6, introduced by Intel in 1986, offered enhanced memory management and a true 32-bit architecture. The concept of instruction pipelining and integration of caching during the 1990s played a crucial role in achieving higher processing efficiency. Caches with hierarchical structures and multi-megabyte sizes aim for high heat rates to mitigate performance penalties. Cache coherence protocols manage synchronization between caches in multiprocessor systems. The integration of caching and pipelining during the 1990s laid the groundwork for today's sophisticated computing systems, emphasizing the crucial role of software optimization as processors evolve in complexity. Now, let's proceed to the simple as possible one or SAP1 operations. The simple as possible one or the SAP1 microprocessor serves as an educational tool designed to illuminate the foundational principles of computer architecture. Operating on a clock mechanism, SAP1 ensures that each operation aligns with clock pulses, establishing a structured rhythm for processing. In the fetch cycle, the memory address register holds the instruction's address, initiating a memory read operation signaled by the control unit. The content of the address memory location resides in the memory buffer register, subsequently transferred to the instruction register. Moving into the decode and execute cycle, the control unit decodes the opcode from the IR, determining the operation to be executed. Specific registers including the accumulator, B register, input register, and output register are activated based on the opcode. The ALU performs basic arithmetic operations with operands from the accumulator and B register, storing the result back in the accumulator. The load and store operations involve transferring content between the accumulator and memory locations, exemplified by load accumulator or the LDA and store accumulator or the STA instructions. Input and output operations facilitate the exchange of data with external devices utilizing the input register or the INR and the output register or the OUTR. Jump and control operations such as jump or the JMP and conditional jump modify the instruction sequence influencing the program counter. Increment or the INX and decrement or the DCX operations adjust register contents while the halt operation or the HLT stops the processor. The control unit orchestrates these operations by generating control signals based on opcodes directing the flow of data and instructions. This one includes a clock reset mechanism, synchronizing operations and resetting the system for subsequent cycles. This intentionally straightforward architecture of SAP 1 provides a robust educational foundation for comprehending microprocessor fundamentals. Paving the way for more intricate architectures, it aids learners in grasping essential concepts such as instruction cycles, data movement, and basic arithmetic or logic operations within a computer system. For example, imagine you are using a simplified computer system based on the simple as possible 1 or SAP 1 microprocessor. Let's say you input a program into this system to perform a basic calculation. First is the LDA05, means load the content from memory address 05 into the accumulator. Next is the add06, means add the content from memory address 06 to the accumulator. Third is the STA07, means store the result back into the memory address 07. And the out or the output the result. Then last is the HLT, means halt the processor or ending the program. Now let's break down how the SAP 1 processes these instructions. First, in the fetch cycle, the program counter points to the first instruction at memory address 00. The memory address register holds 00, initiating a memory read operation. Then the content at memory address 00 is loaded into the memory buffer register and then transferred to the instruction register. Next, in the decode and execute cycle, instruction 1 or the LDA05, the opcode LDA is decoded by the control unit and the memory address register is loaded with the operand 05. The control unit signals a memory read operation and the content at memory address 05 is loaded into the accumulator. Next is the decode and execute cycle. The instruction 2 or add 06, the opcode add is decoded. The memory address register is loaded with the operand 06. The control unit signals a memory read operation. The content at the address 06 added to the accumulator. Fourth is the decode and execute cycle. The instruction 3 STA07. The opcode STA is decoded The memory address register is loaded with the operand 07. The control unit signals a memory write operation, and the result in the accumulator is stored back at memory address 07. Fifth is the decode and execute cycle, or the instruction for out. The opcode out is decoded. The content of the accumulator is moved to the output register for display or further processing. And the number 6 is the decode and execute cycle, the instruction 5 HLT. The opcode HLT is decoded and the processor is halted, ending the program. In this example, the SAP1 efficiently executes a basic program that loads two values from memory, adds them, stores the result back in memory, output the result, and then halts. This illustrates the fundamental operations of the SAP1 microprocessor in a simplified context. Now, let's proceed to our last topic, which is the simple as possible one programming. Programming for the simple as possible one or SAP1 microprocessor involves creating a sequence of instructions to perform specific tasks. The SAP1 architecture is deliberately simple, making it an ideal platform for educational purposes to understand the fundamentals of computer programming. Here's a basic overview of SAP1 programming. First is the instruction set. SAP1 has a limited set of instructions, typically including operations like load, store, add, output, halt, jump, conditional jump, increment, and decrement. Second is the memory addressing. Programs are stored in the memory and instructions are fetched and executed sequentially. Memory addresses are specified in the instructions to access data or specify location for storing results. Third is the accumulator usage. The accumulator or the AC is a central register for arithmetic and logic operations. Most operations involve loading data into the accumulator, performing operations, and storing results back. Fourth is the jump and control flow. Jump instructions or the JMP alter the flow of the program by changing the program counter. To jump to a specific memory address, conditional jumps allow branching based on certain conditions like 0 or carry flag. Fifth is the input and output operations. Input operations involve loading data from external devices into the input register, while the output operations move the data from the accumulator to the output register for display or further processing. Sixth is the data movement. Load or LDA and store or STA instructions facilitate the movement of data between memory and the accumulator. Increment and decrement instructions adjust register contents. And last is the halt operation. The halt operation or the HLT instruction stops the processor, ending the program. Here's a simple example of a SAP1 program to add two numbers and display the result. LDA05 means load the first number from the memory address 05 into the accumulator. Next is add06 means add the second number from the memory address 06 to the accumulator. Then STA07 means store the result back into memory address 07. Out means output the results, then halt the processor. In this program, the SAP1 fetches instruction from memory, performs arithmetic operations in the accumulator, stores the result back in memory, outputs the result, and then halts. This simple example illustrates the essence of SAP1 programming focusing on basic arithmetic and control flow operations. In conclusion, we've journeyed through the fascinating landscape of CPU evolution from its nascent stages to the advanced processors of today. Our focus on the simple as possible 1 or SOP1 architecture has unveiled the fundamental functions and programming principles that form the backbone of computing. Armed with tangible examples, we've illuminated complex concepts, offering a comprehensive insight into the intricate world of CPU architecture and programming. Thank you for watching.